Hello, everybody. I'm going to stand for this part. So I'm Ekaterina Dineva. I am a postdoc at KU Leuven, and I am a solar physicist by education. So my part here will be to talk to you a little bit about the big picture. So basically, all these predictions, all these phenomena that we try to study, where they come from, how they propagate to Earth, and basically how this heliosphere exists with the sun creating this kind of environment for all the solar system. And for the focus to be on the presentation, I'm gonna sit down here, and if you have questions, it's perfectly fine to just interrupt me, and have your right. So quick outline. So we are going to start with the big picture, the heliophysics. We're going to go down to the sun, and then we're going to expand what's coming from the sun to Earth. And then we're going to talk a little bit about data sets, and maybe later in the day about certain type of flare forecasting with certain data set and certain focus. Okay, why do we need to know that? So there is a phrase going around more and more that we are studying system of systems. So each one entity in this in a solar system is a system by itself, but it's part of the larger system, being the heliosphere. If we understand the physics, of course, or the processes behind it, we can pose the correct questions, and we can basically find the new problems to look for. So on the other side, all that you have heard so far is about using certain data sets to create certain models, to include in models, to do prediction, and so on and so forth. So there are certain constraints on our data set. So we measure what we know, basically. So you don't measure what you have not thought about measuring. There is also a certain data selection that you have to do, and it is good to know your instrument and where your data coming from. And of course, there is pre-processing that happened before you get the data, which you also have to be aware. So certain data sets are more useful for for certain tasks, where other data sets are very, very good, but they are not fitting for the task that you mean. For example, there are these new instruments going on. They're new, they're shiny, they have amazing data, but they have like short-term observations. You don't have large time series, and this is an issue, for example, for to create prediction models, but on the other hand, you can study special cases with them. So all that is basically all the information that you have to be aware. I'm not saying you have to know it, because it's impossible to know all that, but you have to be aware of these things. Next. Right. Okay. So the heliosphere, our sun basically creates an environment, a plasma sphere of a sort, through its solar wind expansion or solar corona expansion. It depends how you want to frame it. Again, it depends on your scientific problem. And then basically you have the inner part where most of the planets are, and then you have a terminator shock between you and the interstellar wind. So these are energetic particle from outside of our system. So in a sense, our sun is protecting us from the influence of the highly radioactive particles from outside of our systems, for example, from supernova remnant, like a very special case, but everything from the outside, creating an environment where we as a species can exist, and also we have a stable system of planets. Here I have put additional information, but that is later on you have this slide, so you can also go through this. And of course, all the space weather, all the propagation of particles, radiation, and so on and so forth is happening in the central part, basically, that we care about. And space weather is often referred to where Earth is, like near Earth environment and between Sun and Earth, but space weather also exists for the other planets. It's quite interesting as well, but this is FYI. And basically cool stars, sun-like stars with a certain dynamos and certain winds create this kind of astrospheres. So heliophysics. So it's a like very composite way of studying everything that is happening in the solar atmosphere, solar system. So we have what's happening at the planets, what's happening in the interstellar space, at Earth, which most of you probably are more concerned. This is also applicable for astrophysics, for other stars as well, as I said previously. So heliophysics and heliosphere basically combines all that huge information. And we have quite a lot of instruments flying around. So this is not the updated version, of course, unfortunately, because of certain political situation. Not all of these missions have been prolonged or happened, but let's say that quite a lot of the important ones, like basic key projects, are either ongoing or are funded to happen. So the information is coming from everywhere, from near Earth, from in between, and closer to the sun. Our just this, as it's mentioned, this shiny new instrument, Solar Orbiter and Parker Solar Probe, which are getting closer to the sun, and then basically sampling from the corona as close as we have ever been before. And as I mentioned, space weather happen also around other stars, planets. So we have here our focus a lot on Mars, and on Mars a lot currently. Right, I mentioned system of systems here. So I think at this point everybody know what the sun is. And it is a system of itself. It's layered from the interior of the sun to the exterior, and we are more interested in the exterior. So it has basically three prominent atmospheric layers. So there's photosphere, chromosphere, and corona, and they are separated by the plasma conditions, so density and temperatures. And also, because they have different plasma conditions and different densities, you have also different magnetic field configurations in that. So in the photosphere, we are intimately aware by sunspots. It is first thing that we see about the active regions, which are the producers of space weather triggers. And then in the chromosphere, it's a little bit more complicated, and it's probably the most complicated layer to study and to model and to interpret. So a lot of people just assume it as a hot wall, basically, between the photosphere and the corona. And of course, in the corona is where our reconnections happen, our flares, and where the solar wind basically propagates outwards into the solar system. So we have different phenomena. We have the sunspots. And for example, if we look in the corona, you have hot loops, which are sources of intense UV radiation as well. And then you have plages, which is basically what is happening. It's like bright features between the corona and photosphere, yes, in the chromosphere. So what I want to say, there's a lot of things happening at the same time. So one active region, I think Eduardo was showing these very nice pictures of different wavelengths. So this is not just how it looks differently, it's also in a different heights from the surface and different physics guides what's happening there. So when we combine it, so here I would like to make a caveat: we combine data sets, we have to be aware that they look similar, but they can represent very different physics, and then we have to adopt our modeling and our understanding according to that. Right, so, and of course, one thing we keep in mind, that the solar wind is the entity, I would say, that connects everything in the solar system and provide information about how the magnetospheres are connected to of the different planets, if they have one, are connected to the heliosphere. Okay, a little bit about the sun. So we often say that, so we like to study the most active parts, but this is not technically only time when a high energetic active region had happened. It can actually quite often happens basically at the declining phase here. You can actually, in the solar cycle 24, I think that is, no, 24, 23, 23, basically, in the end of the cycle, there were, so somewhere here, there were like the strongest flares for the cycle, and this is because of how the magnetic field configuration changes during the cycle. So you basically start, so the dynamo inside of the sun creates this, let's start with like approximation. It creates a poloidal field, basically, which goes from one pole to the other. And then inside the sun, you have differential rotation. And the differential rotation is have a radial gradient, so it changes between the core and coming out of the solar surface. And basically, this differential rotation drags the field around to the point where we have this configuration, right? A toroidal field. And because of these different flaws, because you have the differential rotation, but you also have here, if you see, I'm not sure if you see the meridional flaws, because they're in the hemispheres, basically, again, transporting flux, and then this flux basically pushes first of all, it twists the magnetic field, then pushes it out, and at some point, due to buoyancy in the convection zone, this is like just the layer before the surface, it rises up and creates these active regions. So on top of creating these active regions, it pushes the magnetic field around, right? So for the next cycle, we accumulate, again, the field as a poloidal field, and then we also switch the polarity. And this switch, I will talk later, is related to certain laws of the cycle. But we basically have the 11-year cycle, which is very convenient to remember. This is activity cycle. So you have here, this is a very nice image from Soho Observatory. So you start with very quiet sun, and then you build up to a lot of these basically active regions emerging, and then you go basically relax down, and this happened over 11 years. But so you start with certain polar distribution, and then it switches and the next cycle it switched back. So we call this a 22-year Hale cycle. So these are the most stable cycles. There are other cycles over hundreds and even thousands of years that people try to model and try to understand. But these are the ones, I would say, also relevant for the human lifetime. There is a nice link when you can see basically how different the sun looks in the EUV, basically this one. But Eduardo showed it last time, and I just leave it here so you can play around. There is a very nice data center from ESA and NASA. So during this cycle, we expect most activity, obviously, to happen near the solar maximum. But it's very interesting, the rising part of the current maximum was also already populated with more X flares and stronger X flares than the entire previous cycle, which was like a little bit abnormal low activity cycle. So how this, like basically how this dynamo works and how it accumulates and relaxes magnetic field and then again accumulates the poloidal field is very important to predict what kind of activity actually you're going to have in the next cycle. So sometimes people care about obviously flare forecasting on the level of days or a week. However, if you plan a very important mission, even unmanned mission, so you want to basically be aware in the next decades what the situation will be in the heliosphere. So you try to predict this kind of situation, to plan your mission and plan when to lift off, so on and so forth, because these are not short-term missions. You can prepare something like this for 30 years or so. Okay, so quickly about the what's happening to the active regions in during the cycle. So as I said, you have different the poles are switching, and then you have certain laws about how your active region will look magnetically. So what is the leading or following? So in one hemisphere, basically, in one hemisphere, you have always, or like you should have always one polarity leading and the other following, and then you have a certain tilt between them. They're not just aligned like this. There is a certain way the configuration between the two polarities go on. And then you also have the law about where the active regions start forming. Why am I mentioning this? Because often it happens, that's not true, not often, but sometimes you have abnormal active regions. And these abnormal active regions are believed to be, I would say, disturbing to the entire system. And then they can basically, after that, there can be a follow of abnormal activity, or the next cycle will have a certain amplitude. So we also try to study those. They are rare, but surprisingly very effective at changing what's going to happen in the next cycle. So this is something that one have to keep in mind. And also because yesterday we were talking about data augmentation, right? And then this is basically Sun doing its own augmentation. And when you do solar flare predictions or activity predictions, you don't want to be dependent on the cycle that much. So this is in one way in favor of doing augmentation. Do we change the physics? Yes. Is it natural? Actually, sometimes as well. So doing augmentation means that you catch maybe also some of this abnormality happening and include it in your consideration for the prediction. Just a second. Right. So I was saying solar activity regions looks in a extremely different way, no matter how you look at it. So these are different wavelengths. Here on the top, you have the magnesium lines basically in the chromosphere. And then you have a certain filaments here in a different line. You see them dark or bright, depending or where the line is, where you see emission or where you see absorption. And then it's very interesting to look at Doppler velocity, so basically how the plasma in what you see look like, because, okay, when you see it like this, right? Or like, for example, in the coronal loops, in the first, like when you see it like this, you kind of have the feeling that you understand how it's configured, right? You see the loops, so everything's fine. However, the distance between the loops can be hundreds of kilometers, and also not only on horizontal, but also in vertical direction. So you can have things happening in a very different planes. Then again, you see a different implementation in the photosphere, a different view in the photosphere below. And then you arrived at a very important measurement that we have mentioned many, many times, the magnetic fields, basically, which shows you how so on top you see the filaments or the loops. You see how the plasma moves in between. So you have the blue one is basically material coming toward you. So there is this filament that's for some reason is expanding towards you, and everything else is basically going away from you. This is line of sight. So things are very dynamic as well. So when you do predictions on using coronal images, it's also, you have to be aware of the dynamics. And the photospheric magnetic field, that's why we talk so much about it, because it's very straightforward. There's like line of sight, whatever you see, it is that, basically. So it is a very convenient way to see the evolution of the region and how the foot points of the field looks like. So for example, here it's like an illustration of the different layers. And the foot points are firmly in the photosphere where we measure the magnetic field. And that is a very convenient way to parameterize information about the active region. That's why it's probably one of the most common data sets when you do flare forecasting. Sorry. Okay, yeah. So here, just a little illustration of how that works from SDO. So this is a very interesting, nice, complex active region, which actually consists of three active regions, in the sense that it was labeled like this. So the human labels are the three different, or like human bias labels, even if we have automatic labeling, we still include our own understanding of how this active region should look. And this looks like one region. It's three regions mixing together. Will that be important for the flaring? Yes, because each region have its own history and also flare history. So it's, but will this flare? You don't even need a flare predictive models. Something like this will flare for sure, and not once. So this is how it looks it's called a transition region. Basically, this is a little bit above the photosphere, a little bit hotter plasma. So you can see what you see as a brightness is this basically thin magnetic field tubes, which in the spot, because they're large and they're pushing the convection, they look dark because it's also cooler inside. But when they have a very small radius, they actually heat up and then they appear bright. So this is just exactly the same thing. And this is basically where the flare happens. So we include a lot of the chromosphere, a lot of the photosphere, but the flare will happen maybe 500-600 kilometers above what we are parameterizing, what we are working with. So there is and we don't include the chromosphere that much. It's still a open question how to do that, and basically it's probably up to some of you to figure out how to include it, because basically you're skipping few hundred kilometers, maybe up to 1,000 kilometers, maybe even more, between the reconnection site where the flare happens, basically where the flare happens somewhere here, much above. Then you have a lot of things happening here, right? You have filament channels, which are also connected to the chromosphere. You have, when a reconnection happens, you have propagation of particles in outwards, but also inwards, which falls on the chromosphere and hits it and then produce other type of radiation. So we have from here quite a lot of X-rays. We have a radio, which are important to be also forecasted for communications. So this is, again, a little system forming where we don't have all the answers yet, right, in how to combine all the data sets. So in these slides, there are also a lot of additional information, but I just want to connect what you heard yesterday from Eduardo to basic understanding that we have. So, okay, coronal mass ejections, when we have strong flares and we have some material suspended nearby in the coronal loops. So basically these filament channels with material flowing in and out of it. It can be disturbed through the reconnection and then ejected into outwards, right? It carries its own plasma, so particles, and it carries its own magnetic field, basically often we say frozen in the plasma. So what is so this is an important part which is also discussed when predicting flare in CMEs. There is a certain correlation between strong flares and CMEs, given the condition that there is something to be disturbed and something to be ejected. But we also have CMEs that appear without flares, rarely, but they do happen. I think they call them ghost CMEs, but I'm not particularly sure right now. And we also have CMEs happening from not only X flares, but like lower energy flares. So there is always, like, it's easy to predict, should not say easy, but it is convenient to believe that if you predict flare, you're also predicting CMEs and you can combine that. Not always such a clear picture. And in a recent conference, I was told even not to think about it like this. And then when you predict CMEs, you have to just really focus on that particular phenomena. And just, if there is a flare, there is a flare, that's great. So both flares and CMEs, of course, accelerate some particles towards us. So there's a radiation coming up. And the CMEs come with a bonus magnetic field, which will interact with our planet's field and its outer atmosphere. Right, these are nice images, I think, again, from SOHO. This comes here to support that you are given certain data sets that you can play around, like create this difference images as well. So the input for your models is not necessarily the EUV image or the image as it is, but it provides you with a lot of time series to study CMEs. This particular instrument, which I will mention later. And just for reference, this is one of my favorite pictures. So this is Earth, and this is a CME. So first of all, it's very, very good that we're not close to the sun for many reasons, but one particular reason, because we'll be extremely close to this kind of monsters. Right. So one thing to mention is that when the CME leaves the solar near solar environment, then it's going to be measured as a ICME, so with in situ measurements in between sun and Earth. And so these measurements are often, this in situ measurement are often at this L1 orbit, which is about 0.99 AU. So basically they are very, very far away from the sun and almost near Earth. So basically, we have some missing information between sun and when we measure them at L1. And this is also a question of modeling and predicting the parameters of the CMEs. When basically when you do CME predictions, that it's important to predict what is happening and how it's evolving in between the sun and the Earth. And then I will mention the solar wind in a moment, which is basically what is going to guide the propagation and basically guide what is going to happen with all the materials and magnetic field that started from the sun. And also we have nice cases where you have more than one CME happening and like several ICMEs propagating. I think there was 3 ICMEs, which very interesting case. What was also quite puzzling about that is that all this energy, all these like monstrous CMEs, and the basically the activity detected, geomagnetic activity detected at Earth, was not as like not as strong that people expected it. 3 CMEs and nothing. So there we have to kind of persuade the shareholders, the people who are giving us money to do that, that even if it didn't happen this time, it will happen next time, or it may happen next time. Right. So solar wind. Right. So I think you heard quite a lot of solar wind, and you hear also more about solar wind and modeling and prediction of parameters later. So here I would like to just illustrate how the velocity and intensity and the direction changes quite a lot with the cycles. So we were talking about the cycle. So you have a very nice configuration in the beginning. So the blue and red is like the polarities. I know outward, inward, sorry. But it's also polarity, yes. So in the solar minimum, you have the fast wind basically at the poles, and at solar maximum, the picture becomes kind of irregular all over the place. And then towards the next minimum, it's kind of try to get back to its initial state. But there is a difference. Sometimes people how can I say, they are equating the minimum with the decline phase, which is which may appear similar when you look at the sunspots, but when you look into magnetic field distribution, as you can see here, there's a lot of things happening still. These streamers that goes basically in all directions. So one still have to consider the effects of the solar cycle on their predictions. And again, this becomes even more important if you have a satellite mission with a certain trajectory that you want to put. So this information gets, as I said, important. The differentiation between the stages is important. Okay, so solar wind, as we said, propagates out towards the heliosphere. And due to the rotation of the sun and its magnetohydrodynamic nature, we have the darker spiral, basically this, that's also called ballerina skirt configuration. And this guides the propagation of all these so energetic particles accelerated in solar in flares, the CMEs, and how it basically connects to the heliospheric magnetic field, and how it arrives also its geoeffectiveness, because due to this rotation there is obviously a magnetic drag which pulls the CME and we would basically hit Earth or not. It's like too far away probably. And one thing that yesterday was actually, just by looking at this picture, I realized that because of the nature of Parker spiral, you have also the different space weather severity and different space weather connectivity that in the inner planets and the outer planets, as you can see here. So they're closer to the center of the, so we and the inner planets are closer to the center of the spiral. And this is also where the so-called Goldilocks environment is, where we have liquid water, where life as we understand it can exist. So it is, as I mentioned, other stars have also space weather, and they have astrospheres, and they have winds. So it's very interesting how the most livable part of a system like this is where you have quite a lot of space weather happening. So there can be life, but technology is in a little bit in peril, so close to the sun. So just something to think about. Okay, so actually I'm done more or less with the overview of the heliosphere and of sun and what's happening there. So do you have maybe some questions about that part? Yes.
It's a very basic question, but do we know why the polarity of the solar magnetic
the dynamo. So we have a dynamo models, right? So there are more theoretical in the sense that we have a very good understanding how the dynamo works, but we cannot always make it continue. So it sometimes died out after a few. So when we model after a few cycles, it just stopped starting, which is a bit annoying. Also not my particular field, but the switching happens because of the rotation and the rotation and the flows push this magnetic field around, right? And then not only in the equatorial plane. It also sometimes crosses the equator. But the point of it is that redistribution of the field causes the accumulation of polarities, basically, which causes the switch. And this is also the prescription for it to continue working, right? If you don't have this switch, it just dies out. So, yes.
Thank you.
Another maybe basic question. What is the magnetic field strength in the active regions?
My goodness, I should know that. So, oh my God. Honestly, like, it's really good question, but right now I just cannot think about. Does anybody of you guys remember what's the
Fixed values and
intense in Tesla basically
they usually
several
negative are above 800.
a few hundred also. Yeah,
The house
right.
1,000 can go to up to 4,000. Usually the range, the max is about 4,000. Okay. Minus and plus.
And this is in the photosphere, right? That's yeah. And then it becomes more complicated because in the photosphere you can actually measure it, and in the chromosphere and the corona you have to interpolate it from with certain modeling. So yeah, that's why we also like to work with the photosphere, because we actually can infer the field and when you go higher in the chromosphere and corona, it's becoming a bit more complicated to infer it in the same way, in a bulk way, so you can use it in this way. Yesterday was shown a very interesting observation, but these are ground-based observation, because at the ground base you can include a lot of spectroscopy and a lot of polarimetry, right, in different wavelengths. And they showed me something that they called chromospheric magnetograms. I still wait to see what that is. So things are happening while we speak.